Hi guys, so I'm going to tell you a little bit about how a triple quadrupole works today and tell you about the parts and how you use it to fragment and identify molecules. So a triple quadrupole, the basic unit of the instrument is made out of a quadrupole, which looks like this. It's got 4 rods that are evenly spaced across the length of the instrument. There's another one sort of out here in the plane of the board that you can't see. But if you were to look at this from the side, you would see 4 rods like this. If you were to look at it from the side, you see something like that. So what happens is each of these rods has either a positive charge or a negative charge, and they're opposite one another here on the device. And at some time 0, you have a charged particle, an ion, flying into this rod. And when it does, it's attracted to the opposite charged rod. So it starts to fly towards this rod. It starts to bend away towards this rod here, for example. But what happens is, the electronics in the instrument are precisely timed such that when the ion gets close to that rod, the polarity switches to a positive, negative, negative. And then the ion that had flown to here is all of a sudden repelled because it's coming close to a like charge. And so it flies off towards the other rod. Well, after another unit of time, the instrument switches polarity again. And so after it switches back again, the ion finds itself right next to this rod, which is repelled again. And so it starts flying off towards the next rod. And so what the net effect is that this particle will end up gyrating down this instrument all the way out. Okay? All right, so why do ions respond to changes in the electric field? And that can be understood through basic Newtonian physics. There are 2 definitions for force. One, which you all learned in high school, force is equal to mass times acceleration. The other definition of this, which you may or may not have been exposed to, is that it's proportional to the charge of a particle multiplied by the electric field a particle is experiencing. So using these 2 classic definitions of forces, you can actually come to understand why the particles respond in a mass to charge kind of way. And you can get there just by rearranging this equation. You say that the acceleration of a particle, so the derivative of motion with respect to time, which equals the acceleration, is equal to the charge of a particle by the multiplied by the electric field divided by the mass of the particle. Right? So what does this say? This says that how quickly something responds to an electric field change is proportional to the charge of the particle and inversely proportional to the mass. So what does all that mean? So if you go back here and look at our quadrupole, you've got positive charges here, your negative charges here. You've got your ion sitting here in the middle. You've got 2 different flavors of it. If they're the same mass and the same charge, they will respond equivalently to changes in the polarity on these rods. They'll move towards them at the same rate. But if one of these has got 2 positive charges, this guy will move at twice the rate that this guy will. So likewise, if you have a very massive particle with the same charge as a smaller particle, it will move much more slowly in response to these changes in these changes in the electromagnetic field. So what does that mean? That means that we can control how quickly charged ions move in the gas phase simply by manipulating the electric field. It also means that we can distinguish different particles on the basis of their mass to charge ratio simply by manipulating this electric field, which is something we can do in electronics. All right, so how do we turn this into a mass spectrometer? Well, let's go back and consider our case now where we have our 4 quadrupoles. We know now that how quickly an ion responds to an electric field is proportional to its charge over mass. So how quickly it will move towards one of these rods is a function of those two things. So if we have a constant charge, let's say, like this particle will, all the particles will eventually run into that rod. But as I said before, these things flip in polarity back and forth from negative to positive. So if you were to look at the polarity on this rod over time, this being time here, see the polarity does this. It alternates, oscillates back and forth between negative and positive charges. So what that does here is for very small particles, they still run so quickly towards this pole that they just run into the rod and they get destroyed. And very, very large particles barely move because they're so massive. They don't respond very quickly to these changes. And things that are in between will cycle all the way down between the quads over time, just as we showed here. So that's cool because that creates a situation where you can have a mass filter. So just by setting the electric field, this oscillation rate properly, you can make it such that anything lower than a particular molecular weight, or m over z, is filtered out. All the small stuff is destroyed because it runs into the quad, and all the big stuff makes it through because it's sitting in the center of the instrument. So this is allowing you to create a mass filter that only allows large masses through. Well, as it turns out, this oscillating current isn't the only one that's applied to a rod. There's a small constant current where there's a small constant bias for a particular rod, say this guy here, to have a constant partial bias towards positive, and this one to have a constant partial bias towards negative. So even though these rods switch back and forth in their polarity like this, there's still a little bit of an offset here that's always biasing it towards a net positive charge for a particular rod. This is a DC current, direct current. And what that does is over the long term, although this large particle here is circulating in the middle of the quadrupole and flying down the middle of the quadrupole, doesn't respond very quickly to these oscillating magnetic fields. It does respond to this sort of constant pressure, and what happens is over time this large particle will start to oscillate closer and closer and closer and closer to the rod. It'll bend towards the rod, and eventually those large particles will large particles that are too big for the electromagnetic field range will destroy themselves on the side of the rod. So what does that mean? If you get this thing set right, you can have a small area here where anything that is any particle that is too large is filtered out because this magnetic field, this constant magnetic field, pulls them towards one of the poles. And that leaves this cool little area in between. If you set your oscillating and constant electric fields right, where you can select out a particular mass that you want. And the resolution of that for a quadrupole is about proportional to 1 m over z. All right, so here's our next topic. We know how a single quadrupole works, how it filters mass. And now the question is how you turn that into a mass spectrometer. So if you've got your quad here, we'll redraw it quickly. We know now that the quad, what it allows you to do is filter out ions with a particular m over z. And it's a pinhole that only allows a particular mass to charge ratio through. So in a triple quadrupole, you actually have 4 of these quads. So you have another one right behind it, just like this. This in this instrument here, or in this particular quad, you leak in a small amount of nitrogen, and then the masses that are allowed through collide with nitrogen gas, and when they do, you get a spray of smaller particles, of smaller ions, and these are all different mass to charge ratios. Those come out the back of the instrument. Well, you can filter for a particular particle using yet another quadrupole. And this looks just like the first two. And this one just like this. You can use the setting of the electric fields here to select out a particular mass. And then now at the end of this whole process, you started with an intact molecule, you fragmented it, and you selected out a particular product mass, and now you want to detect it. At this point, you've only filtered masses and fragmented them. So the way you detect it on a typical triple quadrupole instrument is that you would have a metal plate back here, and what happens is as soon as this particle strikes that plate, it'll induce a current, a small electric current that you can detect with like a voltmeter, for example. And that usually goes to an electron multiplier, and that's how you actually detect the signal. So in summary, a triple quadrupole is a mass spectrometer with 3 quadrupoles. The first and the last quads are only used as mass filters, and the mass filter works by just setting the electric charge here such that you only get a particular m over z through the instrument. And you use this instrument typically by selecting for a particular parent mass, fragmenting it, and then isolating a particular fragment or product mass, and you detect it because it smacks into an electric plate, or I'm sorry, a metal plate that induces an electrical current that you can detect. That is how a mass spectrometer works.